Hello students, in this video we'll see how to compute the flux of a vector field over a surface. So if we're given a parameterized surface, S, I'm just going to write down its parameterization over here. R of u and v is its parameterization, with u and v residing in some parameterization space, D. Then the flux of v, of a vector field v, over S is, let's write down the flux formula, flux of v over the surface S, which I'm going to write with this notation. It's going to be a surface integral of my vector field. I'm going to dot my vector field with the normal vector, the unit normal vector, RU cross RV, over what? Over the length of RU cross RV. So now that's the unit normal vector to the surface. Okay? And then I'm going to do d sigma over here. And so what we do with this measure over here, this of course is a vector. I call this whole quantity over here d sigma hat. So you can write these surface integrals as the surface integral of v dot d sigma vector. Now we should note, of course, that since d sigma is RU cross RV du dv, what this will simplify to is this flow integral will simplify to the double integral over d of v on the surface R of uv dot RU cross RV du dv. So all we're doing over here is we're just dotting the vector field on the surface. That's a dot product, not a multiplication. Since this is a vector and this is a vector, this is a dot product. Over there, that's a dot product. And so all we're doing is we're just plugging in the vector field. We're taking the surface and plugging it into the vector field and dotting that with RU cross RV, which is the unnormalized normal vector to the surface. Okay? So that's what the flux is. Of course, what does this look like geometrically? If you have a surface, here's my x, my y, and my z, and we have some surface like this. There's our surface, nice and regular, right? Just bent surface. There's my surface over here. And if there's a vector field, what we can do with this surface is at every point on this surface, we can compute a normal vector. Sometimes it's longer than others, sometimes it's shorter than others, longer vectors. But at every point, I can compute a normal vector pointing directly at the surface. So those are my normal vectors. Those are these things over here, the normals. And then I'm given some vector field. Now the vector field might be all over the place, right? It might look like this, like this, like this, like this. There's my vector field. And of course the vector field is at some point going to match up with what? Is going to match up with our normal vectors, making some angle with some of them. There's my vector field. And so what we're doing is we're measuring, in some sense, the dot product of v. So this is my vector field. Remember, when you dot two vectors, what are you doing? When you dot two vectors, you're measuring the cosine of the angle between them up to their lengths. So what I'm really doing here is I'm really computing the cosine of the angle in between these things over here. So we should stop and think when this flux will be large. So our flux will be large Our flux is large when the angle between v and RU dot RV, cross of course, is small. Okay? So when the angle between RU and RV is small, RU cross RV and v is small, then these vectors from the vector field line up with the normal vectors and we get a very large dot product. When it's close to 90 degrees, we get a very small dot product. So the flux is small. Flux is large when the angle between v and RU cross RV is close to 90. because then the dot product is 0. So if your vector field is actually flowing along the surface, then your flux is very, very, very small. However, if you're in line with the normal vector surface, if you're trying to exit the surface, then your flux is going to be large. So that's the flux is a measure of how fast you're traversing the surface, if at all. Okay? So let's see an example of computing flux. Let's find the flux of this vector field, x, y, z, that's my vector field v, over this plane. Z is equal to, let's do this, let's do a 10 minus 2x minus 5y. Okay? So what we'll do is we'll parameterize our surface. So how do we parameterize this plane? Well, it's very similar to before. So what we have over here is, let's draw our plane. There's my z, there's my y, and there's my x. And so here's the point 10. Now, of course, if y is equal to 2, there's a 2 right there, there's a 5 right there. I just connect these dots over here. There's my plane right there. Right? Okay? And of course, with the parameterization space is this triangle in the xy plane. Right? This triangle over here is my parameterization space. Okay? So my parameterization space looks like this. That's a y, that's an x. This, of course, is a 2, and that's a 5. So this line over here is y is equal to 2 minus 2 over 5x. So that's our region over here. That's my parameterization space. So let's parameterize this sphere now, or this plane now, rather. So if I parameterize this plane, I'll have r of u and v is equal to x will be u, y will be v. Then this will be my parameterization space. And then what will z be? It'll be 10 minus 2u minus 5v. And where do u and v live? Well, u is between 0 and 5. That's my x. And my v is between what? My v is between 0 and 2 minus 2/5 of u. So that's my parameterization space. Now, what's RU going to be? So RU is going to be 1, 0, negative 2. RV is going to be what? RV is going to be 0, 1, negative 5. Let's cross these things. What's RU cross RV? That'd be IJK. And then 1, 0, negative 2, 0, 1, negative 5. So my I entry will be 2, so we're going to get a 2. Then what will my J entry be? My J entry will be a 5. And what will my K entry be? My K entry will be a 1. So 2, 5, 1 is RU cross RV. Now we can set up our flux. So what's our flux? Our flux is going to be the double integral. So where does u go from? U goes from 0 to 5. That's my u. What does v go from? V goes from 0 to 2 minus 2/5 of u. 0 to 2 minus 2/5 of u. And then I plug in what? I plug in my vector field, which is x, y, z, and I dot it with 2, 5, 1. So what's x on the surface? X on the surface is u. What's y on the surface? Y on the surface is v. And what's z on the surface? Z on the surface is 10 minus 2u minus 5v. And I have to dot this with 2, 5, 1, dv, du. And so last bit we'll do is just set the double integral, and we'll leave it as a double integral. Integral from 0 to 5, integral from 0 to 2 minus 2/5 u. Let's dot this. I'm going to get a 2u from u times 2. I'm going to 5v plus 5v plus 1 times this. So that's going to be plus 10 minus 2u minus 5v dv du. And so what happens over here? Well, the 5v cancels, the 2u cancels, and I just have 10 times this area. Well, what is this area? The area of this triangle over here. So I'm just going to have a factor of 10 times the area of that triangle. And so what's the area of this triangle? It's going to be, the base is 5, the height is 2, so base times height is 10, divided by 2 is 5. So I'm going to have a 10 times 5, so this flux is just going to be 50. Thank you very much.